Hey guys, welcome to AP Physics C Mechanics. This is Ms. Whiteley. Welcome. You're going to be using these videos as your lectures since I can't really teach two classes effectively lecture-based at once. But if you have questions about the material in these or you really need me to explain something in a different way, feel free to come ask me and we'll get things worked out. But these videos are going to be your main source of learning besides the textbook. Today's lesson is going to be on velocity and how it relates to displacement. So we'll also cover what displacement and distance are. And then we'll also kind of look into different types of velocity. There's average velocity, instantaneous velocity, relative velocity, how all of these things are different, how they're all similar, and how we can handle them mathematically. Velocity is covered in our textbook, which is University Physics by Young and Friedman. We're going to be using the 15th edition, not that it really matters. Textbook editions are mostly scams. And velocity is going to be in chapter 2. It's going to be sections 2.1 through 2.2. You'll note I am skipping chapter 1. Chapter 1 is mostly tools that need to be in your toolbox from previous math classes or that sort of thing. If we need those and when we need those, I'll give you tutorials on them as they come up. If you want to look through it, feel free to look through it. A lot of it is vector methods or stuff about units, stuff about conversions, prefixes, all that kind of stuff. So as we need it, I will talk about it. If you want to go work through that chapter just for your own edification, great. So in this class, we are doing calculus-based mechanics. And the cool thing about calculus-based mechanics is that it is actually a lot easier to do than algebraic physics because calculus is a really, really powerful tool that was literally developed for physics. I think the best way to study physics is always to start concepts with definitions, so we know precisely what we're talking about. In order to get to a definition of velocity, there's a few other definitions we need to know first. And the one we're going to start with is position, which I'll define as an object's location in n-dimensional space. And the reason I say n-dimensional is because this could be one-dimensional, two-dimensional, or three-dimensional, or even if you want to go further than that, it could be fourth, fifth, however many dimensional. It's best to have in physics as general of a definition as you can that's still precisely what you're talking about. Now, position is a vector. Most often in physics, it will be represented by an R. Why it's an R for position? Don't know. You can maybe think of it as kind of like radius with an arrow. So the arrow means it is a vector. Now the second arrow I'm drawing here is just my own notations. This R with the arrow is how it would actually be written in an equation. For example, if on a number line, this is my number line, if I plot my object to be here at 3, I could say my position R equals 3. Hopefully at this point in your life, you know that a vector is a quantity that has both a magnitude and a direction. So you may be wondering how an object's position in space has a magnitude and a direction. After all, the object is just sitting there doing nothing, just chilling. And the way that that works is with an origin, okay? So here on my number line, I have a place that I have marked as 0. And in any coordinate system that you use to define a position, one-dimensional, two-dimensional, three-dimensional, any of them, you always have to have an origin, which is kind of like an anchor. It's a place that we define arbitrarily. You can really choose it to be anywhere, but we define it to be 0. If it's one-dimensional, like my number line here, it's just a single 0. If it's two-dimensional, like on an XY plane, it's the coordinate 0, 0. Or if it's three-dimensional, which we can get by adding another axis in here, it would be 0, 0, 0. So it's just 0 for each coordinate that's possible in your n-dimensional space. Here in my one-dimensional number line, my origin, is just a single 0. And since my position is 3, my vector points from 0 to 3. You'll notice the tail of the vector always starts on the origin, and then the point of the vector ends up on our position. So we've got a direction. It is to the right, which is positive here on this particular number line, and its magnitude is the length of that vector, which is 3. So going from origin to position, we have both a magnitude and a direction, so position is in fact a vector. Now that we have defined position, we can also define displacement. Displacement is a change in position. So this word change we're going to be seeing a lot all over the place in physics. It's everywhere. So it's represented symbolically as the Greek letter delta, which just looks like a triangle. So displacement is a change in position. We could notate that as triangle for change, or delta for change, in position, which is our vector. So this is the general notation for change in displacement. A lot of times in introductory physics or in 1 or 2 dimensional physics, you'll see this also written as change in x or change in y if we're only moving in the x direction or the y direction. If we're going to 3-dimensional, you can also have change in z. But when all of these things come together, you've got a change in x, a change in y, and a change in z. They are generalized to this change in position or change in the r vector. Now the delta or change itself is what we could call an operator. So an operator is a symbol that represents some operation happening to the thing that's right after it. So in this case, it is a change in position. Change is the operator, the thing happening. Position is what it's operating on, what it's happening to. So the delta or change as an operator means that something is different between the end and the beginning. And we'll note those as RF for final minus RI for initial. Now, the F and the I are what you're used to. They're familiar, they're comfortable. But frequently in physics, you will also see it notated as R prime, which is like the apostrophe for final. That means after. And then minus R with no primes, which indicates that it is the initial. And then it can also be notated, a third notation, we love notation, as the change in R is R, which is what it currently is, minus R sub 0, or that's also written as R, or called R naught. The little sub 0 is a naught. So in this case, the R naught would be the initial position and the R would be the final. So it's kind of ambiguous there, because this symbol is in both places. So you really just have to be heads up on the notation that your author is using, or your lecturer in this case. I tend to favor this bottom one down here. So let's go ahead and see that in an actual scenario. I've got my lemur here on my number line at position 3. So to begin with, his position, his R vector, with a little naught or 0 to indicate initial, it's equal to 3. And it's a positive 3. I'm not going to put the positive sign here, but it's positive 3, which means it's to the right of the origin. So I'm going to go ahead and notate that as a vector here on my line. I'm going to do it as a red vector. So I know that doesn't look like a very straight vector. It goes from 0 to 3, and it's got a magnitude of 3. It's got a direction to the right. Very simple. Position vector is 3. Now, if my lemur dude moves, we're going to ignore the fact that he's hopping way over everything, over to -4, his new position, or final position, is going to be equal to -4. So this is where it gets a little bit tricky. So his position vector has the same definition as all other position vectors. It starts at the origin and it moves towards the position, which is at -4. Now, if I want to find his displacement is the change in position, which is the operator R final minus R initial or R naught. And I can go ahead and do that here mathematically because I've got some nice numbers. Our change in position equals R, which is -4, minus R naught, which is 3. -4 minus 3 is -7. And you can, in fact, see if he moves from 3, which is where he was, to -4, that vector is in the negative direction. It's moving left, and it is a length of 7. Now that might seem like a really drawn out way to say the lemur moved 7 spaces, but we need to do things precisely here so that when they get a little bit more complicated, we'll know what's going on. All right, so we have now defined position and we've defined displacement. Now our last thing to do is define velocity. Velocity is defined as an object's rate of displacement. Ooh, forgot the apostrophe there. Okay, all better. Now, the word rate here means changes with time. Changes with time, or maybe changes over time would be a better way of saying that. But we do have a change here, a nice delta, and this time it's time, which is our classic lowercase t. The very imprecise definition is how fast something is going, but the very precise definition is the rate of displacement, how displacement changes with time. And you have classically seen this represented with the equation velocity equals change in x over change in time. And now we're going to tweak that a little bit to match our new notations. So I'm going to move that guy over. And our new notation is going to be velocity with an arrow because it is a vector. It equals our change in position or displacement divided by change in time. And change in time is not a vector. I guess you could say time flows directionally, but we're not dealing with all of those shenanigans. Time here is just a typical scalar. So if we go back to my lemur here, same scenario. The lemur started at 3 and then moved over, not the whole timeline, just the lemur, moved over to -4. We've got our displacement vector was equal to -7, and that negative holds the direction. To find a velocity, we would need to know how long that takes. So it started at position 3 when time was equal to 0. Now if I say it took 2 seconds to get over to -4, we'll end over here at time equals 2 seconds. We can then find the velocity. Say the velocity equals the rate of change of the displacement, delta r over delta t. Our delta r is -7. We already figured that out. Now the delta t acts like an operator once again. You always need to be able to do the delta operator. It is final minus initial. So our final time was 2, our initial time was 0, so it's just 2 minus 0. We've got -7 divided by 2 is 3.5. Oh, and it's a -3.5. Now we do need units on this. I have been ignoring units thus far. Let's bring them in. So our unit for displacement is usually going to be meters. I'm going to make it here as meters. And then our usual unit for time is seconds. So to get meters per second for velocity, you have your -7 meters divided by your 2 seconds. So that's meters per second. To get your final unit, you can do the math on the units exactly as you would with numbers, just instead as units. If you don't know how to do that and that doesn't make sense to you, come talk to me and we'll walk through it together. So our velocity there is negative 3.5 meters per second. The negative indicates that the lemur moved to the left. Now here is the problem with that. Say I have Mr. Lemur Dude. Okay, we're going to take Mr. Lemur Dude back over to his initial position. And Mr. Lemur goes from 3 to negative 4, not the timeline, need lemur. Goes from 3 to negative 4, straight there, takes the 2 seconds, and is all fine and dandy. We can easily describe his velocity there as negative 3.5 meters per second. That makes sense. But here's the problem. If we take Mrs. Toucan here, and she starts at 3, just like the lemur did, but if instead of flying straight to negative 4, she goes really fast, gets tired out, and then goes really, really slow to negative 4, but still takes the exact same 2 seconds, we end up with the same result, that she was going negative 3.5 meters per second. Because she would have the same displacement. Oh, that's a lightsaber. I thought it was just going to be a regular pointer. Woo! Okay, so if our toucan here had the same displacement, because we went from 3 to negative 4 over the same amount of time, her velocity is negative 3.5 meters per second. Well, the deal is that didn't really describe exactly what the toucan did. The toucan went really fast and then slowed down, so it maybe was never even going negative 3.5 meters per second. So it's hard to say the velocity of the toucan is negative 3.5. And that's because this equation, that velocity is change in displacement divided by change in time, is simply the average velocity. It will not tell you in between the 2 points what the actual velocity was. So it's called the average velocity. Even though the toucan and the lemur had different velocities in between, their average velocity was the same. So the new thing that we're going to be learning about velocity that is specific to AP Physics C, or calculus-based physics, is instantaneous velocity. Instantaneous. Yep, that's how you spell it. It's a monster of a word. So instantaneous velocity is the velocity at any particular instant along an object's path. It is way more descriptive than the average velocity because it will tell you the velocity at any point in time of the object rather than just the average. And instantaneous velocity is defined mathematically as velocity equals the derivative of the position as a function. Now, the harder thing about this definition is it means you have to have the position as a function of time. So it's not just 2 coordinates like we saw over there. You had the sloth began at 3 and ended at negative 4. You have to have its whole motion as a function. For example, I've written a function here, r sub s, which is the position of the sloth as a function of time. Now, if the sloth moved linearly, the equation for that motion is negative 3.5t plus 3. And you can see that this works for the sloth's motion because if we take that function at 0, its position is 3. Negative 3.5 times 0 plus 3 is 3. And then if we take it again at 2, which was our second time where we observed the sloth, you'll see that negative 3.5 times 2 plus 3 is negative 4, which is where our sloth ended up. So that function accurately describes the position of the sloth at a particular time. Now we're going to take a brief segue into some graphing here with these. Let me scoot those over. So you can see here on the graph, we've got that position function graphed. It starts at 3. At 2 seconds, it's at negative 4. And you should remember from your previous physics class that slope of a graph is equal to its velocity. So you can see that by looking at rise over run. So the rise here is your delta r, and your run is your change in time, change in position divided by change in time is equal to slope, which here is equal to velocity. So the slope of your line is equal to velocity, and slope of a line at a point is exactly what a derivative finds. So if we take the derivative of our function, we find the velocity. So velocity equals derivative ddt of the function, which is negative 3.5t plus 3, and it is with respect to time. And so you should know by regular derivative rules that the derivative there is negative 3.5. If you can't do that derivative in your head, take a second, pause the video, work the derivative out so you see that the velocity is in fact negative 3.5. And so we get this both through our original formula and through our instantaneous velocity formula. Now for the sloth, the average velocity and instantaneous velocity were the same because he moved at the same rate the whole time. But we'll see for the toucan, things will be a little bit different. Now we're going to be looking at the toucan. So the toucan in my previous scenario had kind of more like a piecewise function where it went really fast and then went really slow, but it was kind of going fast at the same rate, then slow at the same rate. I am going to do something different than that here for our function because I don't want to deal with a piecewise function and I don't think it's going to be as applicable. This time we're going to say that it is more of a quadratic. Now, because I picked really gross numbers, our equation is going to be negative 7/4 t squared plus 3 as the function to make it work out, where you have 3 and negative 4. So if we look at r for toucan at time 0, negative 7/4 times 0 squared plus 3 is 3. And then if we look again at 2, that is going to be negative 4. So it works out to be the same total displacement there. But if we look at our velocity, it's always changing with the toucan because we said velocity is slope. So in a quadratic, the slope there is always changing. But to find the instantaneous slope at any place, we use a derivative. So the velocity function for our toucan is the derivative with respect to time of negative 7/4 t squared plus 3. Now to do that derivative, it's not quite as trivial as our last one was. You do power rule, multiply 2 times negative 7/4, you get negative 7/2. Lower the power by 1 to get t, and your constant term goes away to 0. So our velocity function for the toucan ends up being negative 7/2 times t, and you can see it's dependent on time, it changes with time. So for example, at time equals 1, halfway through the run or the flight for the toucan, you'd have velocity equals negative 7/2, which is in fact equal to the average velocity. But if you did something like velocity at 1/2, you'd end up with negative 7/4, which is drastically different than negative 3.5. So you can see that the instantaneous velocity is going to end up being quite a bit different than the average velocity. But the main takeaway here is that our new definition of velocity, because most of the time you're going to want instantaneous, is that velocity is the time derivative of the position function. And those are both going to be functions of time. So your velocity you're going to be looking for is a function. Your position is going to be a function. And then if you want to know where an object is or how fast it's moving at any specific point in time, you just plug that time into the function to pop out the numerical value for velocity or the numerical value for a position. So we're going to go ahead and do an example from the book. This is example 2.1. It says a cheetah is crouched 20 meters to the east of a vehicle. At time t equals 0, the cheetah begins to run due east toward an antelope that is 50 meters to the east of the vehicle. During the first 2 seconds of the chase, the cheetah's x-coordinate varies with time according to the equation x equals 20 meters plus 5 meters per second squared times t squared. Find the cheetah's displacement between time equals 1 and time equals 2. Find its average velocity during that interval. Find its instantaneous velocity at t equals 1 by taking delta t equals 0.1 seconds, then so on, so on. Derive an expression for the cheetah's instantaneous velocity as a function of time and use it to find velocity at t equals 1 second and t equals 2 seconds. So we'll start with part A. Part A says find the cheetah's displacement between time equals 1 second and time equals 2 seconds. So we're looking for displacement, which we know is delta r, or change in position. Now, in this particular example, they're assuming we're only moving in the x direction, so they have specified that's going to be our delta x. So the notation is changing a little bit just to specify we're only looking horizontally here with that delta x. So to find delta x, we need to know the x at time 1 and time 2. Now they haven't given us the two positions. They have given us the equation for the x, and that equation is that x equals 20 meters, I'm going to leave out units here, plus 5t squared. That's our x. So to find x at time 1 and time 2, we just need to plug those times into the equation. X at time 1, which is 1 second, equals 20 plus 5 times 1 squared equals 25. And then x2, which is at time equals 2, equals 20 plus 5 times 2 squared, which is 5 times 4, which is 20, so we get x2 equals 40. And then that delta x operator means that we're doing our second position 40 minus our first position 25 equals 15 meters. So the cheetah between 1 and 2 seconds went 15 meters. So all we did was took the position x, the function of it, and found at two different times where the cheetah was. Subtracted them to get the displacement. So we're done with part A. I'm going to move it up here, get rid of it for a second. Okay, part B. Find its average velocity during that interval. We know that the average velocity is simply delta x divided by delta t. So our delta x we just found to be 15 meters divided by the seconds. So the number of seconds that was from 2 to 1, so that's just 1 second. And that equals 15 meters per second. Now part C, I'm not actually going to do on screen for you here. If you want to, you can try it. It's simply getting close to the instantaneous velocity by doing smaller and smaller time intervals. So you could do the same process we just did, find the displacement and then find the velocity by doing time 1 equals 1 second, and then doing time 2 equals 1.1, so doing small interval, and then time 2 equals 1.01, so on and so forth, and you get closer and closer and closer to the instantaneous velocity. I'm not going to do all those computations here for you, because honestly it's a waste of time since we've got the big boy of the derivative that will straight up just tell us the instantaneous velocity. So I'm going to get rid of C here. Should have picked a bigger eraser. And go straight for D. Derive an expression for the cheetah's instantaneous velocity as a function of time and use it to find velocity at time equals 1 and time equals 2. So the word derive here seems really scary. It's not at all. We're just going to take the derivative. That's what deriving kind of is. So we know that the velocity instantaneous equals the derivative with respect to time of our position function. And we know that function is, where did it go? 20 plus 5t squared. So to find the instantaneous velocity, all we need to do is take the derivative of that bad boy. Derivative of 20 with respect to time is 0. Derivative of 5t squared is 10t. So that is the expression or the function for the instantaneous velocity. velocity equals 10 times t. And then we can use that to find the velocity at 1 second and at 2 seconds. So the velocity at 1 second is velocity with 1 for t. So we do 10 times 1 equals 10 meters per second. And then velocity at time equals 2 is simply 10 times 2, plugging it straight into the expression we found, and that equals 20 meters per second. So to recap what we learned, we defined position, displacement, and velocity, and we learned the difference between average and instantaneous velocities and how to numerically calculate them. So that's all I've got for you on velocity. I did mention relative velocity at the beginning of the chapter. I'm not going to go into that in this video. We will talk about it at a later date. But if you got any questions, let me know. You should have some practice now to cover with velocity.